Okay, we're going to talk a little bit about Jupiter's amazing moons. Here you see a very rare thing. It's very easy to see a transit of one of Jupiter's large moons. And a transit is like an eclipse. It's when the moon passes in front of Jupiter, and you can often see the shadow. Here is one moon, and another, and a third, and here you see the three shadows. That's rare to have all three shadows being seen at once on Jupiter, but we've seen at our own astronomy nights the transit of moons before, which is pretty cool. All right. There are 4 large moons around Jupiter, which are sometimes called the Galilean moons, and then a whole bunch of little tiny moons. There are no medium-sized moons for whatever reason, by chance. Here, for example, right there at the upper left is an example of what we call a small moon. That's a typical one of Jupiter's small moons, but the 4 large moons are absolutely fascinating. As a matter of fact, you can think of Jupiter very much as having its own little solar system, if you will. And it's kind of fun to compare its solar system to the solar system at large. So, for example, one thing that they have in common is that the moons of Jupiter all orbit in the same direction around Jupiter. We call that a direct or prograde orbit. They are nearly circular orbits, also very similar to the planets, and they are going in a flat plane, like they're riding around on a DVD. So all of that would all be a similar thing in number 1 there, similar to the solar system at large. Now, Jupiter's 4 moons are tidally locked. As you recall, that means as they go around Jupiter, the same face is always towards the planet. Is that true of the planets and the sun? No. There's not a single planet that is tidally locked with the sun. You would think Mercury might be, but of course it is not. So that's a big difference, number 2 there. The density of the moons. You start out with heavier, rocky moons like Io and Europa, and then you finally get out to icier moons like Ganymede and Callisto, and the density decreases. Is that similar to the planets around the sun? Yes, it is. We have the 4 rocky planets that, remember, we're talking density, not mass or size. The actual density is great. They're heavy. And then you get out to the lighter gas giants. So that is a similarity. So 1 and 3 are similarities. 2 is a difference. How about this one? The orbits of the moons are actually, 3 of the 4 anyway, are in resonance with each other. What does that mean? Well, it means that Io goes around Jupiter exactly 4 times in the time that it takes Europa to go around twice in the time that it takes Ganymede to go around once. If you're wondering, Callisto is the odd man out. Callisto is much further away than the others, so you'll see that in the telescope, in a backyard telescope, and it's not in the grouping there. So 3 of the 4 are in sync with each other. They're in resonance with each other, like gears in a clock. Question: are any of the planets in resonance with each other? Now the answer is no. No, we're not in resonance with Venus or Mars or anything like that. Now, there is an interesting resonance. The answer to this would have been yes years back, because Pluto is in orbital resonance with Neptune. So by the time Neptune makes 3 orbits around the sun, Pluto makes exactly 2. So we do have examples of resonance, but technically speaking right now, I would just say this is more of a difference than a similarity, if we just put it that way. Here are the 4 large Galilean moons in comparison to our own moon. So you see our moon is smaller than Ganymede and Callisto, and just slightly bigger than Io and Europa. I mean, just looking at them, you see how interesting they are, right? How different they are. Look at Io and the coloring there. Really fascinating. So let's get right to it and talk about Io, the most active object in the whole solar system, geologically active, which is amazing because you would think far from the sun you would not have something so active, but we do. And just look at the coloring. Now that comes mostly from sulfur. You have these active volcanoes spewing out. I'm going to throw in the fact that it's the most volcanically active, and I'm going to go ahead and make this call, that it's probably the worst smelling place in the solar system. It's going to smell like sulfur, like sort of rotten eggs all the time on Io. About the same size as our moon. So we're going to have to answer the question, how can it be so active? It's far from the sun. It's a little cup of coffee. Seems like it would have cooled off, right? They were stunned When Voyager 1 flew by in the 1970s, to find 8 volcanoes erupting at once, just incredible. I mentioned the sulfur already. Because of these active volcanoes, we consider it to be a very young surface because it gets repaved all the time. Matter of fact, the maps would be different. Now, this gets a little fuzzy here, but does it have an atmosphere? Well, yes, technically so. But let me point out, it doesn't really have enough gravity to hang on to an atmosphere permanently. The only reason it has an atmosphere is because it always has volcanoes erupting and spewing out things like sulfur dioxide. That's fine. We still count it as an atmosphere, I suppose. But just keep in mind, if the volcanoes quit, the atmosphere is gone. It can't stick around. There's one of the volcanoes. This one's called Pele, after a god, not after the soccer god. So there's Pele erupting near the equator. Here's a more recent eruption. Look at that, right off of the pole there. That's amazing. That has to be stretching, you know, hundreds of miles there. Remember, low gravity, these plumes can go really high and really far. It's pretty neat stuff. Beautiful picture there. You see the terminator line of Jupiter and the terminator line of Io, and you catch a little bit of a plume there. Probably that same volcano erupting. Just fascinating. Now, check this out. This is pretty neat. The plasma torus, or what I call the space donut. The plasma torus, you have these volcanoes erupting, and they're spewing out particles, and some of those particles are going to be charged particles. Well, Io is sitting right in the heart of Jupiter's super powerful magnetic field. And so these particles get swept up in the magnetic field. They stay. They don't fall back down to Io. Basically, Io has left a trail of debris around Jupiter. It's a ring, but not like a typical ring of ice and rock. This is a ring of charged particles, something very, very rare and kind of unique here to the Io Jupiter system. Pretty neat, the plasma torus. And so that doesn't count as Jupiter's ring. It does have a ring that's separate from that. Io would be a tough place for us to ever visit, even with unmanned stuff, because it's right in the heart of that magnetic field. It's getting pummeled by charged particles. It'd be a pretty nasty place, not to mention that one side you're freezing, and if you're, you know, close to a volcano, you're burning up, and it's just, it's a wild and tough place there to visit, dangerous place. So how can it be so hot? That's really the big question. Here's what we think. We think the fact that Io is being sloshed around as it goes around Jupiter. We call it tidal stress. Tidal stress. It's just like the moon pulls out our tides. But in this case, Jupiter's mighty gravity has really stretched and pulled and compressed little Io so much that it's heated up. It's kind of like taking a wire. If you bend a wire back and forth enough time, you build up enough internal heat that wire can get really hot. And so that's what we think. As Io gets thrown around in an elliptical orbit, stretched and squeezed and stretched and squeezed, it builds up heat due to tidal stress. That's how a moon this far from the sun and this small can still have heat, which is very, very surprising. That's why it was such a surprise, but now we know. Now we know. There you can see a little bit of that plasma. You can actually photograph that plasma torus, that ring of particles created by little Io. Little Io. There it is. One last look. Look at all the interesting sulfur compounds and stuff. Really one of the most fascinating places in our solar system. I think I'm going to save the other moons for next time. Thanks for listening.